Again, this is 16.1 illuminance, talking about light. Light travels in straight lines. It's particle-like and wave-like, but not really either. We can kind of show you that it is both particle-like and wave-like. I can show you a shadow. If I put the shadow really close to the projector screen, we can see that it is very crisp on the edges. But as we move this thing away, you can see that those edges get blurred. And that's because light is diffracting around the edge of the meter stick. And that diffraction is a property of a wave. So we know that light acts like a wave. Now light is also particle-like because it can transfer. It transfers and you feel heat, so it's interacting with matter. Particle-ish. When we draw light, we usually draw it as a ray, which is just an arrow. It looks like a vector. The speed of light was first hypothesized by Galileo to be a finite speed, meaning that it has a speed limit. This is as fast as light can travel. When we talk about the speed of light, we're usually talking about it in a vacuum. That means it's not going through air or water or glass. When it goes through these mediums, or media as they call it, it will go a different speed. And a diamond is the slowest that the speed of light will go. Maybe that's why it's so sparkly. In 1670, a guy named Romer actually made very precise observations of Io, and he found that depending on the time, like whether it was spring or winter or fall or summer, that Io its eclipse across Jupiter would take a longer amount of time. And he found that depending on where Earth was, when it was closer versus further away, he found that it actually took 13 seconds longer. So light had to travel from wherever Earth was here all the way over here, and that took an extra 13 seconds. So using that extra 13 seconds, he was able to calculate the light to be about 2.2 times 10 to the 8 meters per second. And this, again, was in the 1670s. That's long ago. Right now, we've come up with more precise calculations with lasers and technology and things. And we found that light to be closer to 3 times 10 to the 8 meters per second. But for the 1700s, that's not really too bad of a number. So light sources. We have a couple of vocabulary words for you today. We have a luminous source, which is also called luminous flux. So luminous flux, or luminous source. This is whatever's producing the light. So it could be a sun or light bulb. It's producing the light, creating it, emitting it. And then we have illuminated source, which is a luminance. Now, the reason it says luminous source and illuminated source is because this is what appears in your book. But then when they ask you in the problems, they call it luminous flux and illuminance. They're the same things. They're just a little tiny bit different when they're talking about the wording of the problem. So this is up here, what you're going to see in your problems. That's what they're talking And this is the surface that's reflecting the light off of it. So it's what you see. Pretty much everything in this room here is an illuminated source, or it has a luminance, because we can see it, the light's bouncing off of it. The only thing in here that's a light source would be the light bulbs. That's your luminous flux. And then there's one more that's not up here, which is in the next slide, I'm pretty sure. And it's called luminous intensity. And it's close to luminous flux, and it's close to luminous source. But this one's just talking about how bright it is. Brightness. Now, if you remember in the sound lab, we talked about medium. Medium was what the sound was going through. So was it going through air? Was it going through water? Was it going through train tracks? When we talk about light, we talk about media. Same thing, same idea, just a little bit different words, so we talk about it with light. With media, we have three different types of media. It's either opaque, transparent, or translucent. And when we think opaque, we think about those like maybe a filter or a film where you can kind of see some light through it, but you can't really see anything through it. That's not the opaque that we're talking about here. Opaque here is like the surface of this lab bench. We can see it, but we can't see through it. Transparent is like the air in this room. No light is reflected whatsoever. All the light goes through the air. And translucent is like the glass. We can see through the glass, but if we get close to it, we can see the reflection. Or we don't have to be close to it. Sometimes we can see the reflection without it. So we see outside the window, but we can also see some reflection. Same thing with water. We can see into the water, but we also see a reflection from the stuff above it. So that's translucent. Some light comes through, then some reflects. Okay, let's give you your first equation. We'll start with the three different things that I've written on the board here. Luminous flux, that's your luminous source. Illuminance, this is how much light the surface is reflecting, your illuminated, reflection. And then the last one, luminous intensity, this is your brightness. Now looking at the units, luminous flux is going to be in lumen. Illuminance is going to be in lux. So lux does not go with flux, which is weird, but that's the way it is. It's flux and lumen, and then illuminance and lux. Flux does not go with lux, even though we'd like it to. And the last one is candela, and this is your brightness, and you don't see this too terribly often, so don't worry about it that much. But candela is the amount of light one candle emits 1 meter away. So it's just kind of like how bright is things. We would compare everything to the candela, the candle. So the brighter it is, it's more candles put together. So our first little equation talks about this luminous intensity. Now, there's no unit or no variable for luminous intensity. So you just have to write luminous intensity, or brightness if you want. It's going to be equal to P over 4 pi. P is your luminous flux. And it's, remember, how much light is being, or whatever's producing the light, so it looks like a light bulb. So P is your light bulb over 4 pi. So let's look at a picture here to help you. Sun is a luminous source. This would be your luminous flux. The Earth and the Moon are illuminated sources. They reflect the light. They don't produce the light. So when they're reflected light, that is going to be your illuminance, or the illuminated source. And then the last thing is the brightness, the luminous intensity. Now, the luminous intensity would be 1 meter away from the sun. How much light is that? All the way around the sun. So that's, the sun's really, really bright. That's going to be a lot of sun. That's just kind of your brightness. Again, Candelaria. All right. Last equation for you is the point source illuminance. So we're going to use this illuminance. It is E. And remember, illuminance is the light that's reflected off the surface. So to remember this one, imagine the light reflecting off the surface of the E. So this is producing the light, and this is reflecting the light. So our equation will be E equals your luminous source, your luminous flux, over 4 pi r squared, where your r is the distance from the source. So if you have like a sign and you have a light bulb, r is going to be the distance from the sign to the light bulb. It's not how big the sign is, it's how far away the sign is. And that should be measured in meters. These 4 pi and 4 pi r squared, they're talking about the surface area of the sphere around the light bulb. So if you're wondering why you keep seeing that, it's related to that number, that pi r squared, and I can't remember what the surface area is, and what volume is different. And just a little reminder off to the side here, this is measured in lumen, and this is measured in lux, and this is measured in candela. And this one's in meters. So when we're looking at this illuminance, light spreads out three-dimensionally, just like sound. Sound is three-dimensional, comes in every direction. The light comes out three-dimensionally as well. So think of a big sphere emitted by the light bulb. And as you get further away, it's going to end up getting bigger and bigger and bigger. So we're talking about luminous flux. We're looking at that distance away, how much light is landing on that particular point. And the bigger the point is, the more light it's going to collect. So if we looked at just like a little tiny circle here, the amount of light that we're going to collect is small. But if we look at a very large area, the light is going to be very big and a lot brighter, because we're collecting more light. This goes back to your telescopes. Stars are really far away. We can't get any closer, or even if we try to get closer, it's not going to make that much of a difference since they're so far away. But if we stare at it for a really long time, we're going to collect more light. And if we make the surface much bigger, we're going to collect more light. So that's why the telescopes keep getting bigger and bigger and bigger. They have these very large mirrors that reflect light into a lens. And the more light they can collect, and the longer they can collect that light, the better the picture is. And the further they can see, because they can see really dim objects. That's what Hubble's doing. It looks at it for like 9 months straight, and then you can see galaxies. Because they're really, really, really dim up there, but if we look at it for a long enough time, we'll collect enough light, we can actually see it. Perfectly good? Yeah. So luminance. This is what your surface is collecting, right? So as the point source, as your light bulb emits light, the surface The further away it is, the less light it's going to be able to reflect. And this is because as it moves outward, that amount of light is spread over a bigger and bigger area. So think about energy. Light is just energy. If it's really close to it, it's a small sphere, so it's really bright. And as you get further away, your sphere gets larger. So that same amount of light is spread out over a larger area. So the further away you get, the dimmer it gets, the harder it is to reflect that light off of a piece of paper because it's getting further from the light source and not as much light is getting on this part because that light's spread over a larger area. Think about a candle in a dark room. Right next to the candle, it's really bright. You can see, you can read. But when you're on the other side of the room, that light is spread over the rest of the room. And so you can't really see. It's not going to reflect as much light because it's much less. So it's not that it's losing energy, it's just spreading it over a bigger area. Good. Okay. So we're going to do a practice real quick. It says a typical streetlight emits 5 lumen. I'll write that down here. We got 5 lumen. If the light is 4 meters high, what's the illumination of the street? Now help me here with my variables. What's 5 lumen? 5 lumen? P, right. It's luminous flux. It's going to be P. And then 4 meters, what's that? That's our distance, which is R. And what are we looking for? Illumination or luminance, that's E. So we're looking for our equation with P, R, and E. It gives us this one down here. So we have our E, we don't know. We have our P, which is 5 over 4 pi 4 squared. That gives us 0.025, and it is a luminance, so we're going to go with lux. It's not flux. Make sure you watch your units. How do we feel about this? Not too bad. Just plug it into the equation. The only thing that's so hard is when you're reading the problem and trying to decide if it's luminous flux or a luminance, just because they're new vocabulary words. Okay, I have 5 clicker questions for you today. Here is the first one. It says, which media transmits light, but it does not permit objects to be clearly seen? So it's somewhere in between.